Okay, let's dive straight into MotionStream. Real-time video generation with interactive motion controls. This is a really interesting one.
Oh, definitely. It feels like a pretty big step forward for motion-controlled video.
Okay.
They're really tackling the latency issue head on.
Exactly. They basically shift video generation from, waiting around into something you can actually interact with.
And the numbers are quite something. We're talking sub-second latency down to 0.39 seconds in some cases.
Oh.
And throughput up near 30 frames per second, 29.5 FPS. And that's on a single GPU. That's practically real time.
Which is kind of the holy grail here. And it can generate infinite length video too, reacting as you feed it input.
Right. So how did they do? There are a few key technical ideas working together here.
Yeah, the first big one seems to be causal distillation. They take a slower but high quality bidirectional model, the teacher, and they distill it into a really fast autoregressive student model using something called Distribution Matching Distillation, DMD.
And that student model is built differently, right? It's designed for this streaming idea from the ground up.
Totally. They use a specific architecture, borrowing ideas from language models, actually. A sliding window causal attention.
Okay.
Combined with these special anchors called attention sinks and a rolling KV cache. We'll need to unpack those.
Yeah, definitely. And the result of all that engineering, efficiency. Real efficiency.
Constant speed generation. It doesn't matter how long the video is, an hour or whatever, the processing cost per frame stays the same.
Which completely sidesteps the usual problems, like errors building up over time or computation just ballooning as the sequence gets longer.
Okay, so let's dig into that a bit. The ultimate goal, as you said, is interaction. Putting the creator, well, you, in the director's chair.
Exactly. You want to guide things in real time, see the video change. You'd say, move your mouse to draw a path.
And that just wasn't possible before. Not really. These older diffusion models, even the really good ones for motion prompting,
Good near.
they were just too slow.
Painfully slow. The paper mentions synthesizing just a 5-second clip could take, 12 minutes?
12 minutes, that's not interaction. That's like sending something off to render and hoping for the best. Kills any creative flow.
Yeah, that whole render and wait cycle. And beyond the speed, the fundamental way they worked was an issue too.
You mean the non-causal part, the bidirectional attention?
Exactly. They look at the entire sequence, the whole control signal, all at once, start to finish.
So you had to decide the entire path up front before anything even started generating.
Right. No peeking at half-finished results, no changing your mind halfway through based on what you see.
And you couldn't usually generate very long clips anyway. Maybe a few seconds, 1 frames max, typically.
So MotionStream flips that completely. It's autoregressive. It builds the video frame by frame, streaming it out.
Which means it can react to user input, like drawing trajectories as it happens on the fly?
And that performance comparison they give really drives it home, the old bidirectional way. Maybe 0.79 FPS over 100 seconds of latency. The new MotionStream student model, 29.5 FPS, 0.39 seconds latency. It's just a different world of usability.
Okay, so before we get to the clever real-time distillation part, we have to talk about the foundation, the teacher model.
Right. You can't distill a great student from a mediocre teacher. That teacher sets the quality ceiling.
So they built this teacher model first, based on the WAN DIT models, which are pretty well established.
Yeah, and what's interesting is how they added the motion control to the teacher. They were careful not to make it too computationally heavy.
Unlike some older methods, like using ControlNet maybe, which can basically double the processing costs, the FLOPs.
Exactly. MotionStream avoids that heavy duplication. They found a much lighter way.
Using sinusoidal positional embeddings, PE, for the track information, combined with the small, learnable track head.
And then they just concatenate those embeddings with the main video latents. It only needs a tiny change in the first layer of the network. Super efficient.
And apparently this PE head approach wasn't just lighter, it was actually better.
Yeah, better quality and massively faster for the encoding step, like 40 times faster than encoding the track as just an RGB image, which some prior work did. Efficiency right from the start.
Okay, but then there's this creative tension they had to solve. Fidelity versus natural motion.
Ah, yes. If you just guide with text, like drone flying over mountains, you get nice natural-looking stuff, clouds moving, shadows.
But the drone might not follow the exact path you wanted. It might just wander off.
Right. But if you only use the track guidance to force it along the path.
Then it sticks perfectly, but looks weirdly rigid, like it's just sliding across the screen without any real physics.
Exactly, like a 2D cutout being dragged. It loses that natural dynamic feel.
So they blend them, a joint guidance strategy.
Yep, using specific weights they found work best empirically. A higher weight for the text guidance, like 3.0, and a bit less for the motion guidance, 1.5.
To get that balance follows the path, but still looks natural.
And here's a neat technical detail about efficiency again. Calculating that blend in the teacher model actually took 3 passes through the network per step. 3 function evaluations, or NFEs.
Okay, that sounds expensive.
It is. But the magic of the distillation later is that it bakes all that complex guidance logic into the student model. So the student only needs 1 NFE per step. The cusp disappears downstream.
Clever. And they had another little fix, too, for when the track signal drops out, like if an object goes behind something.
Oh yeah, the occlusion ambiguity. Does a 0 value mean it's hidden, or did the user just stop drawing the path?
Right.
So during training, they randomly masked out parts of the track sometimes, setting it to 0 with like a 20% probability.
Right.
This taught the model to keep things coherent, even if the signal disappears for a bit.
Okay, so that's the teacher setup. Now, the main event, the causal distillation, making it fast and streamable.
Right. The goal.
Yeah.
Take that slow, multi-step teacher, maybe 50 steps per frame,
Yeah.
and squash it down into a super fast, maybe even single-step causal student model for that real-time feel.
But just making it causal isn't enough, right? Standard causal models tend to fall apart when you ask them to generate way longer sequences than they were trained on.
Exactly. They drift. The quality just tanks after, say, the 81 frames the teacher was trained on. If you want infinite length, you need rock-solid stability.
And this is where they looked at work from large language models, streaming LLM.
Precisely. They looked at the attention patterns inside their video model and saw something similar. A lot of the attention heads were constantly, persistently looking back at the very first few frames, the initial input image especially.
Like an anchor point.
Yeah, cognitive anchor. It keeps the model grounded in the original scene context.
So that's the attention sync idea. You have to keep that initial context available even as the video goes on forever.
You can't just let the attention window slide completely past it.
So MotionStream's architecture does that. It keeps a local sliding window for recent stuff.
For local consistency, yeah. But it also keeps the tokens from those very first frames fixed as a permanent anchor, the sync.
So the model always has access to that starting photograph to remind itself what the scene looks like fundamentally. Stops it dissolving into noise over time.
Exactly. And to make this work for truly indefinite generation, they used the rolling KV cache.
Okay, the KV cache stores the context, the history for the transformer.
Right. And in MotionStream, as new frames are generated, the oldest frames in the cache, except for the sync frames, are dropped. It keeps the memory footprint constant.
And crucially, they use this rolling cache mechanism with the attention syncs during both training and inference.
Yes, that's the key to bridging the train test gap. It trains the model under the exact same conditions it will face during super long generation. That's why it's so stable.
Okay, stability sorted. But what about speed and efficiency? They did tests on how much context you actually need, right?
They did, and the results were kind of counterintuitive. You'd think a bigger attention window looking further back would be better.
Yeah, more context seems good.
But they found the minimal configuration actually worked best. They call it C3S1W1. A chunk of 3 frames, only 1 sync frame, and a sliding window of just 1 frame.
Really? Just looking back that little?
Yep. Their theory is that looking too far back actually lets subtle errors or accumulated noise from the distant past creep in and degrade the output. Keeping the context super local prevents that drift.
Makes sense. And they handle the time aspect with relative positional encodings, ρPE. So it doesn't matter if it's frame 100 or frame 10,000.
Exactly. The position is relative to the current cache, not some absolute start time. Essential for infinite length.
All right, let's talk performance numbers again, because this is where it gets impressive. On an H100 GPU.
Yeah, the distilled student from the WAN 2.1 model hit 16.7 FPS at 480p. The bigger WAN 2.2 student got 10.4 FPS, but at 720p.
Still pretty fast. But they found another bottleneck, didn't they? It wasn't just the diffusion part.
Right, it was the VAE decoder.
Yeah.
The step that turns the model's internal representation back into the actual pixels you see. That decoding step was eating up a huge chunk of time. like 35% to almost half the total time, no matter how fast the main model ran.
So what did they do? Optimize the decoder itself?
They did. They trained a special, super efficient, tiny VAE just for this.
Yeah.
It wasn't about changing the main model. It was pure engineering optimization on the output stage. Made decoding like 10 times faster.
And that was the final piece of the puzzle for real-time speed.
That was it. Slap the tiny VAE on the 2.1 student, and suddenly you're at that amazing 29.5 FPS with 0.39 seconds latency, fast enough for live interaction, potentially games.
And importantly, the quality holds up. It doesn't look worse because it's faster.
Apparently not. They report state-of-the-art results for following the motion tracks accurately and for overall video quality, sometimes even beating their own slower bidirectional teacher model on motion accuracy tests like endpoint error.
Wow. Okay, so what can you actually do with this in real time?
Well, they showed some cool demos, like real-time motion transfer. Imagine hooking it up to a human pose tracker and having a character in the video mimic someone's movements live.
Or just dragging an object around with your mouse and seeing the video update instantly.
Exactly. But the application that really stood out to me was the 3D novel view synthesis.
Right, where they used it to control a virtual camera, even though it's fundamentally a 2D track model.
Yeah, they generated the 2D control tracks based on depth information, essentially tricking the model into simulating camera movement in 3D space.
And the crazy part is, it worked really well.
Shockingly well. It actually outperformed some dedicated 3D novel view synthesis models like DepSplat and ViewCrafter on standard image quality metrics, PSNR, SIM, LPFPS.
While being massively faster, like 20 times faster than some competitors.
It just shows how powerful good motion condition can be, even if the underlying model isn't explicitly 3D.
Okay, so it sounds amazing, but every paper has limitations. What are the catches here? You mentioned the attention sink.
Absolutely. That fixed attention sink is both its strength and its weakness. It provides amazing stability by constantly referring back to the first frame.
Which is great if the scene basically stays the same.
But it really struggles if the whole scene needs to change fundamentally. Like if you try to have a character walk from a forest into a completely different desert scene, the model would keep trying to pull the visual style back towards that initial forest frame because the sink is fixed there.
So it's not great for, say, generating video from a game where the environment changes all the time.
Not yet, anyway.
Yeah.
That's a key limitation. Also, it still has some of the classic diffusion model issues with really extreme or physically impossible motion.
Like trying to make something instantly accelerate to light speed.
Haha. Maybe not quite that extreme, but yeah, very sudden, sharp movements or things that just don't make physical sense. The model might just deform the object or do a simple slide instead of generating complex, believable physics for it.
And what about the model size? Does bigger always mean better here?
Not necessarily, which was interesting. They found the smaller WAN 2.1 model was sometimes actually better at preserving object structure than the larger WAN 2.2.
Huh.
It suggests that just throwing more parameters at it isn't the whole story. The specific architecture and maybe the training details really matter for robustness, especially with complex scenes or motions.
So wrapping up, MotionStream really does seem like a big deal. It makes video generation interactive.
It transforms it from that passive waiting game into an active creative tool. That infinite-length streaming capability is key. It really validates applying these causal LLM-inspired techniques to video.
And that attention sync idea is fascinating. Proves how vital that initial grounding context is for long-term stability.
Definitely. But looking ahead, if we really want models that can generate continuous evolving worlds, maybe for simulations or truly dynamic game environments.
You need to get past that fixed starting point.
Exactly. The next big challenge isn't just making the models bigger. It's figuring out how to make the attention sync dynamic.
How could the model intelligently decide when the scene has changed enough that it needs to update its anchor frame, its core context?
That's the question. Designing dynamic syncing dynamisms that can adaptively refresh the context when the world fundamentally shifts.
Yeah.
That feels like the next frontier for these kinds of models. Solving that could unlock truly continuous evolving video generation.